Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we'll extend our discussion on liquid level measurement using various pressure measuring elements. So we have covered bellows, Bourdon tubes and thin plate diaphragms. In this video we are going to discuss the same concept of liquid level measurement using another pressure measuring element, which is actually two pressure measuring elements which are similar in nature, which is membranes and capsules. Okay, so before discussing the pressure measuring part, the liquid level measurement part, just a quick recapitulation of the things which we have already discussed. We have discussed membranes and capsules. So basically a membrane is very similar to the thin plate diaphragm, but with the slight difference that membranes are used for low pressure measurements, whereas thin plate diaphragms, they are used for medium to high pressure measurements. So their design, their material selection, their installation for different purposes, it is different as compared to membranes. So they are made from non-metallic materials such as polythene, leather, and in some cases from metallic foils. Okay, and also membranes made from polythene film, which are coated with copper or gold, they also serve as the movable plate in a capacitive sensing elements, the capacitive transducers. Okay, so this is similar to the thin plate diaphragms, but for low pressure measurements and different materials. Okay, similar. So again, the operating principle of the membrane is that when there is a pressure difference on either side of the membrane, okay, let's say this is one side, okay, this is one area where the pressure is applied from this, and this is the other area. So this will be at a certain pressure, and the connecting point which is connected to the source of pressure, as a result of the pressure difference between these two sides, it will either expand or compress. So here the main thing is the pressure from the connecting point is converted into linear displacement of the tip of the membrane. Okay, the tip of the membrane, it undergoes linear displacement like this. Okay, this is the tip. Okay, this is the tip. It undergoes linear displacement. Let me use a different ink, black. Okay, black will be. Okay, this is the tip. It either moves upwards or downwards. Okay, this is the linear displacement in this case. In this case it is this much. In this case it is this much. So depending upon in which direction orientation is placed, it can either be x, y, or z. In this case it is vertical movement, so y. Okay, like this. Okay, because of the pressure difference. So here there are certain things that come into play which gives us the mathematical relationship between the pressure difference and the displacement. So here this is the mathematical equation that governs the relationship between this, which is the pressure difference between the inside the membrane and the connecting point outside, and the displacement. Okay, so it is equal to y equals to r square by 4s and multiplied with the differential pressure. So here r is the radius of the membrane, s is the radial tension, and delta p, which is the pressure difference between the inside of the membrane, in the container, in the encapsulation chamber and the connecting point. So this is the membrane, which is very similar to thin plate diaphragm, but the mathematical relationship is different, and also it is used for low pressure measurements, okay, whereas thin plate diaphragms are used for medium to high pressure measurements. Now the capsules. So capsules, again, like I said, it is similar to the thin plate diaphragms, but here if curved portions or curved elements which are called as convolutions or corrugations, like you saw in the bellows, if convolutions or corrugations are provided to the thin plate diaphragms, then it has greater sensitivity to the applied pressure. It can detect even small variations in pressure and is flexible. So if these corrugations or convolutions are applied to the thin plate diaphragms, we get capsules. So these are the corrugations or convolutions I'm talking about, the curved portions. These are called as convolutions or corrugations, okay, whatever you want to call it, curved portions, okay. This is called as a corrugated diaphragm, okay. It is also a capsule, but it is called as corrugated diaphragm. Now if we apply two of these like this, okay, like this becomes a capsule, okay, on both sides, okay, on both sides. Again, greater flexibility and sensitivity. So it all depends on the the requirement, in what environment pressure is being measured, what is the magnitude of the pressure, what kind of pressure it is, hydraulic, pneumatic, what. So there are a lot of considerations, lot of parameters that have to be taken care of, but for now you just understand, if there is double-sided corrugations on both sides, okay, then it becomes a capsule. If it is on one side, it is called as a corrugated diaphragm. This is a corrugated diaphragm, this is a capsule. Again, the principle is the same. Because of pressure difference inside the chamber and the, so when there is a pressure difference between the inside of the protective chamber or the encapsulating chamber of capsule or corrugated diaphragm and the connecting point, they undergo compression or expansion, okay. This is for corrugated diaphragms and this is for capsules, okay. They expand or they get compressed. So here also the important thing to note is the tip of the diaphragm, the tip of the sensing element. Here, this point, the displacement is measured in terms of this, okay, like this. So the mathematical relationship for the corrugated diaphragm or capsule, that is given by, this is the displacement y, because it is happening along the vertical direction, so we will denote y, okay, this. So the mathematical relationship for the corrugated diaphragm or capsule is given by the differential pressure delta P is equal to AY plus BY cube, where A and B are constants given by A is equal to ET cube by R to the power 4 into A and B is equal to ET by R to the power 4 into B. E is Young's modulus of elasticity of the material which is selected. T is the thickness of the corrugated diaphragm or capsule, the wall thickness, the outside, between the inside and outside layers. R is the radius of the capsule or diaphragm, and A and B they are constants which depend on the material which is selected for design of the corrugated diaphragm or capsule. So this is for corrugated diaphragm and capsule, and this is for membranes. Okay, the mathematical relationship which connects the linear displacement y and the differential pressure delta p. So we have discussed about membranes and capsules, their operating principle. Now we will see how we can use it to sense the level of a liquid. So here, let's say we have a container where we have liquid of a certain density rho, which is known. It is very important. The density of the liquid should be known. It is at a certain height above the reference bottom level H, and there are two conditions again. The lid is closed, the lid is opened. In this case, normal cases, it is open, so the atmospheric pressure is also exerted on the liquid column. So now the pressure exerted by the liquid column, this is given by this, okay, rho g h. So here we have the membrane or capsule, whatever sensing element we have designed, it is the connecting point is connected to this point. So the sensor, it measures the total pressure exerted on it, which is atmospheric pressure plus the liquid column pressure. Okay, that atmospheric pressure is calculated. We get the data from it is constant. So to get the liquid column pressure, we subtract the sensor output reading minus the atmospheric pressure, that value. So this gives us the liquid column pressure. So now when we have got the liquid column pressure, which is equal to rho g h, the liquid column pressure is equal to rho g h. Rho, the density, that is known. Acceleration due to gravity, that is known. This is unknown, which we have to calculate. So in order to calculate the height h of the liquid column, we get PL by rho g. Okay, that's why I said the density of the liquid, the level of which, the height of which we want to measure, that density should be known. Okay, so we get H is equal to PL by rho g. PL reading we have already got from by subtracting the atmospheric pressure from the sensor reading, because the sensor output gives us both the atmospheric pressure and the liquid column pressure. If the lid is closed and there is no atmospheric pressure, the atmospheric pressure becomes 0, then the sensor reading is directly, it directly gives us the liquid column pressure if the lid is closed vessel. But if it is open, both atmospheric and liquid column pressure is there. So from this we calculate the height of the liquid column. Okay, from this simple principle, which is the same for bellows, Bourdon tube, which was then we used thin plate diaphragms, and now membranes and capsule or corrugated diaphragms. Okay. So let us now try to understand this whole thing from a three-dimensional perspective. So this is the membrane. We have the support, the connecting points which connects it to the source of pressure, and then the container or the chamber where it is enclosed. So whenever there is a pressure difference between the inside of the chamber and the outside, okay, the connecting point, the source of pressure here, and the inside pressure, okay, these two pressure, because of the pressure difference, this flexible membrane, it can either expand or get compressed, okay, expand or compressed. okay, like this. And here we are particularly interested in the displacement of this tip, okay, the tip of the diaphragm which undergoes displacement. Same for the other thing, which is the first, the corrugated diaphragm. Here, because of the pressure difference, this corrugated diaphragm, one-sided corrugations on one side, which is called as corrugated diaphragm, it undergoes expansion or compression, okay, expansion or compression, okay. And then for the capsule, okay, same thing. Because of the pressure difference, it can undergo compression or expansion, okay. Okay, compression or expansion, okay, which undergoes the linear displacement of the tip here. This, okay, this. So the same principle, pressure difference causes compression and expansion. So the flexibility, the sensitivity, the material selection, everything comes into play. So what is the magnitude of the pressure, what is the surrounding temperature conditions, everything comes into play. So that is the deciding factor when it comes to what kind of pressure sensing element should be selected for that particular application. Okay, so this is liquid level measurement using membranes, corrugated diaphragms and capsules. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.